Okay, so here's where we were last time. We were talking about systems of differential equations. Remember, for example, like this one, right? So this is a system of differential equations. We're writing it with matrix notation here, but this actually is literally a system. We've got a y1 that's equal to 1y1 minus 3y2, and we've got a y2 prime that's equal to negative 2y1 plus 2y2. So literally a system of equations. Again, coupled. We can't solve the y1 equation because we haven't solved for y2 yet. We can't solve the y2 equation because we haven't solved for y1 yet. So it's a nasty little problem. Okay. This notation makes it more convenient. I developed some ideas last time suggesting that we can think of this not as a calculus-like problem, but as a linear algebra-like problem. And so we sort of showed off how that works by observing, well, look, we're looking for a vector space. We know it's two-dimensional. These two solutions are clearly independent. I have two vectors, independent vectors in a vector space. Therefore, they span my set of solutions. Therefore, all solutions can be written in this form, in other words. And then it's just a matter of kind of rewriting. Take your preference of, how you'd like to write it. Saying that the complete set of solutions is this span, fine. Saying that a fundamental set of solutions are these. Well, it's really the same statement, pretty much, right? Sort of an alternative way to phrase your answer. And one more way to say this, we can say that you can take that first solution, make that the first column, take that second solution, make that the second column, and you'll notice here we're using this fundamental solution matrix that we talked about last time. And again, it seems like sort of an arbitrary thing to take vectors, vector-valued solutions. I mean, these vectors here are clearly solutions. These are things of interest. Why would this matrix be of interest? Just because its columns are interesting, it doesn't immediately follow that it's interesting. But we can see now how convenient it actually is by noticing that this collection of linear combinations here is what you get when you multiply that matrix by a vector of constant coefficient C1, C2. Right, so that's kind of neat how that works. This is a pretty decent argument for why we like fundamental solution matrices. Okay. All right, so notice that was all linear algebra talk, and we're going to be solving these systems as a linear algebra problem. And side note, we're going to find some other uses of linear algebra along the way in doing this. Okay. Let me remind you, I have not given you any idea yet where that came from. I pulled it out of thin air. Right, and likewise, this one, I pulled that out of thin air. This is on purpose, right? I mean, I'm trying to make an impact that look how much linear algebra is going into the solution of these equations. Where these things come from is something we are going to talk about today, and we'll get to it in a little while. Okay, so next thing I want to talk about is particular and homogeneous solutions. Let me remind you real quick, as I mentioned last time, look for continuing analogies, strong analogies between how things are developing here in Chapter 6 and how things already developed back in Chapter 4. And you remember this is one of the theorems that we had back in Chapter 4. If you want to understand all of the solutions to a non-homogeneous Chapter 4 style differential equation, knowing a particular solution and knowing all the homogeneous solutions is sufficient. Right? You just add them up. And by the way, that's great news. It was fantastic news that we could do it this way, because when it comes to actually solving the differential equations, I mean, finding particular solutions, we kind of worked through it. We managed to come up with a way of finding one particular solution, and that's it. Right? It doesn't happen to be that's all we could find. One particular solution. Homogeneous solutions was a nicer story, of course. So it is essential in the Chapter 4 context to be able to infer all the solutions from that one particular solution that you have. Okay. Back in chapter 1, when we talked about particular and homogeneous, that wasn't the case. Right? How do you find a particular solution back in chapter 1? Row reduce. Which goes ahead and solves for all the solutions at the same time. So back in chapter 1, that whole particular and homogeneous thing seems a little silly. Kind of pointless. Right? In chapter 4 is where it really started to pay off. So same deal here in chapter 6. If you have a fundamental set of homogeneous solutions, and then if you have a particular solution to the non-homogeneous equation, right, then the complete set of solutions is what you get by adding homogeneous plus particular. Right? That's the total complete set of solutions is homogeneous plus particular. Okay. All right, so analogous result. Now, do we believe it? Right, is this a true fact, or is this just wishful thinking? This is something that you can prove. You can prove it two different ways. One thing you can do is you can look back at what we did in chapter 4. You can look back at what we did in chapter 1 and kind of, hodgepodge together your own proof, kind of following the template, doing the same kind of things. And that works just fine. You're very welcome to do that. I'm going to show you a different way to prove it, which is to refer to question 5 on our recent midterm exam, which itself is a reference to something that we talked about in class, which is that you can generalize this whole idea of particular and homogeneous. Right? If you have any linear transformation, then you can define, based on that linear transformation, what's a homogeneous solution, what's a particular solution, and we showed through the course of this exercise, which again, likewise, we did in lecture as well. We showed that everything of this form is a solution, and furthermore, every solution is of that form. Namely, that as we're trying to show in this case here, right, that the complete set of solutions is always particular plus homogeneous. Right, so this argument here that it's on the exam, it was in class as well, this proves the result for every linear transformation. So now all you have to do to confirm that this is true in this case, all you have to do is confirm that we have a linear transformation in play, specifically that t of y equals y prime minus ay. You just have to show that this is a linear transformation. Once you show that that's a linear transformation, everything else follows immediately. Okay. All right, so this would be my preferred way to do it. Right? Take advantage of the big. You've already got a big gun. Use the big gun. Don't take care of it. Piecemeal, small tools. Use the big tool. Okay. Let me pause for questions. Anybody have any questions? Everybody okay? All right. Okay. Oh, what am I doing? I hit the wrong button there. Sorry, here we go. Okay, so let's talk about the wronskian. The wronskian looks different for vector-valued functions. And before I get into showing you what the new wronskian is, I'd like to explain why the wronskian looks different. The way I'm going to motivate that is by showing you, in fact, an entire category of new kinds of wronskians. It turns out there's not just one wronskian. There's actually lots and lots and lots of different wronskians. As follows. So here's the question we face, just like we did back in chapter 2. Suppose you have a bunch of vectors. How do you decide if that list of vectors is independent or dependent? Now, in chapter 2, we started off by considering a very special case of vectors in a vector space, namely functions. Right? That itself was already kind of venturing away from the safe waters of, vectors in Rn. If we're talking about vectors in Rn, we know determinant handles that question, right? But if you're talking about functions in some sort of a vector space of functions. How do you do it? It's a hard problem, right? So here and now we're considering an even more general question. These are just vectors in any vector space. No constraints on what kind of a vector space it is. Okay, so we can't, for example, just say, start taking derivatives. Derivatives of what? These might be matrices. They might be colors. They might, I don't know. There's some arbitrary vector space. I don't know what kind of critters these are. Okay, so what do we do? Here's a theorem that we're going to start with. This is an easy thing to confirm. Everybody should do this on your own. But if you have a linear transformation and a dependent list of vectors in the domain, then that will give rise to a dependent list of vectors in the target. This is a very straightforward theorem to prove. If you have a dependent list of vectors in the domain, dependent means that there is a relation. Write down that relation. Take that relation, apply the linear transformation, cite linearity, and what you will have is an explicit relation between the output vectors. Okay, so I want everyone to fill in those blanks, do that argument, and our conclusion is that a dependent list of inputs gives a dependent list of outputs. Now, is this directly relevant to our question? Our question asks if a list of vectors is independent or dependent. Notice that this theorem, as it is, sort of assumes you know the answer to that question, so no, it's not particularly useful as stated here. It doesn't help me if I have to already know the answer to the question I'm trying to answer. Okay, but what we can do, y'all, I'm sure recall, I'm a big fan of the contrapositive construction. If A implies B, then not B implies not A. Right? So specifically, the contrapositive tells you that if you have an independent list of outputs, then you definitely have an independent list of inputs. And now notice in this form, I have a theorem whose conclusion is an answer to the question that I'm interested in. Okay. Now, as of the moment, this is all linear algebra, right? This could be any linear transformation. I didn't say anything yet about functions or vector-valued functions or anything of that sort. Okay. All right. So now let's try to make it a little bit more immediately relevant. If I do want to capitalize, if I do want to be able to talk about this conclusion, if I want to be able to draw this conclusion, I need to be able to first conclude that a list of outputs are independent. And these outputs, where do these outputs live? These outputs live in the target of my linear transformation. So the strategy we're going to take here is I would like to be able to answer this question easily. I would like these outputs to be easily arbitrated as either independent or dependent. So let's have our target be Rn, where it is in fact very easy to arbitrate whether the list is independent or dependent. Okay. All right. So here's the idea then. We know that in Rn, these vectors are independent if and only if those vectors make columns of a matrix whose determinant is non-zero. Old result from chapter 1, I guess it is, right? No, 2, chapter 2. You have n vectors in an n-dimensional space, and there's a whole argument about how that works. But the punchline that we already know is that if this determinant is non-zero, that means that this list is independent. Okay, so let's piece it all together then. What we have is this easily arbitrated computation. That's just arithmetic. If that's the case, then the outputs are independent. If the outputs are independent, we know that the inputs were independent, and therefore we have an answer to our question. So it's a little bit of a ways to go, several steps in that process, right? But an easy observation about how linear transformations preserve relations turns into a test, kind of a test for independence. Now I'm going to call this a wronskian-like construction. It's wronskian-like. Let's see here. Let me circle this. It's wronskian-like in the following sense. When we think back to chapter 2, when we first defined the Wronskian. Here's the thing, that if it's not zero, we get to conclude independent. Right? That is the fundamental property of our original Wronskian that we talked about. Non-zero means independent. Well, this construction does that too. And the beautiful thing about it is, this works for any linear transformation. Right? There's lots of linear transformations out there. And 2 seconds, I'll be right with you. Of course, we do have to have it be vector valued. Right? The output values of this linear transformation have to be in Rn, because I do need to be able to take these output values and I need to be able to make them columns of a matrix. And so it's got to be vectors. Right? But other than that constraint, any vector-valued linear transformation gives me this Wronskian-like construction that does what I want. Yeah?
So do we call the Wronskian-like construction the Wronskian, like in general, or do we call it something else?
No, so the Wronskian is this thing that I have circled in green here. Okay. It's the determinant of the matrix whose columns come from the linear transformation. Right? But the linear transformation itself is... we didn't really give it a name. It's the transformation that makes the Wronskian, I guess you could say. Yeah, right. Good question. Anybody else? Are we good? Okay. So, lots of different Wronskians. Alrighty. So let's think back to chapter 2 for a minute. We didn't approach the Wronskian in this way at that time, but now that we're here and we have this point of view, I claim that effectively what we're doing is we're using this linear transformation. We're using that as our T. This is the thing whose values become the columns of which I take a determinant to make my, in general, Wronskian-like construction, which you'll notice here is the exact Wronskian that we developed back in chapter 2, again with a different motivation there. But so you can see our original Wronskian is a special case of this more general construction. Special case using this linear transformation. Okay. All right. Which, by the way, so that I'll bring you to a point of view. The colleague of mine who used to teach this class a long time ago makes the observation that, well, then why do we care so much about this thing? Why is this the Wronskian? It's just one of these constructions. There's infinitely many Wronskians out there. What's so great about this one? Right? And so his little silly joke along these lines is he would call this the wronskian. It's super. I know, right? I mean, it's clever. It's painful. Okay, so there's that. I will point out one thing. This construction, this Wronskian here, does have a certain key feature. This Wronskian, and only this Wronskian, behaves nicely when it comes to solutions to differential equations. Remember, there was the original chapter 2 Wronskian, and then we have a supercharged Wronskian theorem. If you're talking about solutions to a certain kind of differential equation where various conditions are satisfied, existence, uniqueness, and all that, then the Wronskian takes on superpowers. Right? Do all of the Wronskians do that? No. Just this one does that. And the reason why, roughly speaking, and I don't want to get back into the weeds, but roughly speaking, the point is that this linear transformation, notice, looks a lot like the formula for initial values. And we have an existence and uniqueness theorem for solutions to initial value problems, right? So this particular linear transformation, because of that nice little dovetail, does give us a uniquely capable wronskian. The other ones don't in general have that extra superpower. Okay. All right, so here we are in Chapter 6. We're looking at a whole new category of functions. Let me go back over to here. Here's the things, what they look like now. These are not scalar valued functions like what we saw in Chapter 4. What do you suppose would happen if I took a candidate basis of these and started just taking derivatives like we did back in Chapter 4? It's not hard to see. You would find yourself with too many functions. You can't make a matrix out of the values and derivatives of these functions. You'd have 8 functions. And that's too many. It's too much. It doesn't fit in there, right? Okay. But let's look at this now from the point of view of this approach that we're taking here, which is, why in Chapter 2 did we take all these derivatives? Anyway, well, we took all of those derivatives because we needed to make a vector-valued linear transformation. We just needed it to be vector-valued. And the f that we started with wasn't vector-valued, so I'm going to have to do something that makes a vector. Thus, giving us, this construction here. So here we are in Chapter 6, and the functions that we are interested in dealing with, they're already vector-valued. So I don't have to do anything to them. Or you might say, I apply the linear transformation, which is the identity transformation. And lo and behold, vector valued, right? We have vectors that come out because, of course, vectors went in. Right? So that's the big idea. We're going to use this linear transformation, aka we're not going to do anything at all to our candidate functions. And notice that gives us this formula for our brand new wronskian. Our wronskian is this. The columns of this new wronskian, well, they're just, whatever your functions are that you're interested in. No derivatives necessary at all. We already have enough entries. And again, this is just a special case of our general wronskian-like construction right here. Okay, so that being said, there's our formula, and again, it turns out, and again, I wish we had more time. I'm afraid we don't. But this is not just a random wronskian either. This is also one of those superpowered wronskians, and namely, there is also a extra powerful theorem. If you're talking about solutions to differential equations, if you're talking about solutions to these first order homogeneous differential equations, these functions all solving the same system there. There's 2 possibilities. This is just like it was back in Chapter 4. The wronskian might be identically 0, in which case dependent, or that wronskian might be never 0 and therefore independent. And these are the only 2 possibilities. You will never have a wronskian from solutions to one of these differential equations that is sometimes 0 and sometimes non-zero. It's just not possible. Okay. If you're curious why this is true, I'll be happy to walk through the argument with you. It's it takes a little. It's a 15-20 minute conversation, but let me know. We can certainly do it. But you're not responsible for it. The proof is. To be honest, the proof is just like the proof from Chapter 4, but that is also a hard proof, right? So we're just going to modify that Chapter 4 argument, and it's just a bit much for me to do in class. Okay. So easy example. We were looking previously at this differential equation here, right? And we found some solutions, and we asserted that they were independent. It was pretty clear that these are independent. Let me go back to it. It's pretty clear that these are independent because, after all, they point in different directions. This first one points in the direction of -1, 1. The second one points in the direction of 3, 2. They're like this. Clearly independent. But let's suppose we hadn't gotten that lucky. Let's suppose it wasn't immediately obvious. this test does it for us. There's the first solution. There's the second solution. Notice, as per this formula here, you just take your solutions and make them columns. Punch up that wronskian. The wronskian is the determinant of that matrix, and notice, as promised, it's not sometimes 0 and sometimes not 0. Right? In this case, this function is never 0, and so the solutions are independent. Everybody good? All righty. Okay, so moving along to 6.2, we're going to start talking about how to figure out where those solutions actually come from. Where I got those solutions, I pulled them basically out of thin air. Where did I get that from? And likewise, where did I get that from? Or do I just have to, consult my inner oracle every time? No, of course not. No, so there's a way to do it. It's a nice trick. I'm going to show you the argument. It's a very clever argument. We're going to start off with a special case. Namely, we're going to start off with this matrix assumed to be diagonalizable. Now, this is where the analogy with chapter 4 kind of breaks down. We made no such assumptions. Nothing even analogous to that particularly, right? But something really nice does happen here if it's diagonalizable. And so we're going to start off with just considering diagonalizable matrices. By the way, do notice, of course, constant coefficient. Right? Just like in chapter 4, we consider the constant. Most of the work that we're going to do from here on out is now constant coefficient. Okay. So what is the diagonalizability bias? Diagonalizability allows us to do a change of basis to simplify a matrix. Let me talk about what this means. If you have a diagonalizable matrix, the matrix might be kind of crazy looking. But if you do a change of basis, if you do just the right change of basis, or if you do just the right conjugation, but I prefer to think if you do just the right change of basis, the result will be something that is diagonal, and that is a much simpler matrix. Diagonal matrices are really nice. So what we're hoping here is that, this isn't a matrix, but it's got a lot to do with a matrix. Might it be that simplifying this matrix in a nice way, might that allow us to, in effect, simplify the system? So let's give it a try and see what happens. Here we go. So here's our diagonalizable matrix. Remember, that's what it means to be diagonalizable. Don't forget what this P matrix is. Let's see here. This P matrix. This is the change of basis matrix from V to S, where this is the basis of eigenvectors. Right? Okay. And that being the case, the matrix is a conjugate of a diagonal, and that diagonal is a conjugate of the original matrix. Okay, so what I'm going to do is I'm going to take this formula for A. I'm going to put it right in there, like so. And now here's our new system. Is that better? It's not clear how this is better, right? But okay, now next thing I'm going to do a little bit of algebra. I'm going to take this P and move it over to the other side. Now, of course, you got to be careful. Can you really do that? Well, do remember P is invertible, and this little shortcut we like to think of is moving it to the other side. And really, what I'm doing is multiplying on both sides of the equation. On the left, multiplying by P inverse. So yeah. Multiplying by P inverse on the left on both sides. Effectively, you're sort of whipping that over to the other side. And the result is this. Now, is this necessarily any better? And at a glance, not immediately clear, because again, it still looks pretty weird. There's a bunch of stuff going on in here. P inverse is all over the place. Right? Here's the clever move then. The clever move is to just give P inverse Y a name We're just going to call that Z. Keep in mind, P is a change of basis matrix, therefore P inverse is a change of basis matrix. So really, we're just doing a change of basis on Y. These Y numbers are, these are numbers in Rn, right? These are vectors in Rn, coordinates with respect to a basis. These Z vectors are just coordinates with respect to a different basis. P inverse being as it is, literally a change of basis matrix. As such, the equation becomes like this. And now we can ask, is this any better? Absolutely. This is way better. Huge win, right? We took a diagonalizable matrix, coefficient matrix, and now we have a diagonal coefficient matrix. And that's an easier matrix. So, it's a good news, bad news thing. The bad news is this is a system of equations for something I'm not directly interested in. I'm not actually directly interested in Z. Okay, but once you know Z, it's easy to solve for Y. So the fact that we've turned a hard equation into an easier equation of other variables is still a big win. Okay, before I go on, questions? Everybody good? It's a neat move. All right, let me show you a little bit more explicitly why this is a big win. So this is a diagonal system, we call it, this being a diagonal matrix. Why is it so easy to solve? Well, if you take this system and write it out one equation at a time, we've done this a few times, right? You take a matrix form for a system, rewrite it as, just a bunch of equations literally as a system. This is what you get. You get a bunch of easy equations. And let's look at these equations individually. That equation right there, which you might call the Z1 equation, it's only got Z1s in it. Right? The problem that we had at the start of all of this, the thing that makes all of these systems so hard, is that everything's linked to everything else, right? The Y1 is in the Y2 equation. There's Y2s in your Y3 equation. There's Y3s in your Y1 equation. Everything's in everything else's business. You can't just solve one of the equations by itself. It's got other junk in there. So you couldn't solve the equations individually one at a time. Now we can. Right, look at this. Z1 prime is lambda 1 Z1. That's calc 2. That's a natural growth equation. Not only can we solve it, we have solved it. Right? You can just write down the answer. So, and likewise for all of these other equations, et cetera, et cetera, et cetera. This last one, that's natural growth in this nth variable, Zn. Okay. All right. So a term that is used here is that this system is decoupled. The idea there is, going back to our original sort of metaphor of everything links to everything else, and that we've got a great big tangled web mess, rat's nest of equations all involved in all the other equations, and now that's all gone. We've combed through all the knots, and we have a bunch of independent, unrelated equations. I can solve Z1 without giving a second's thought to Z2. And vice versa. So the term people use is the system's been decoupled, and that's kind of the motivation for that terminology. Okay. All right. So it's all downhill from here. There's some details I'm going to walk through of what once you get to this point, how do you write the solutions, and then therefore how do you work back to figure out what the Y solutions are that we're actually interested in. But this is the big point. All right. So to our original question, change of basis, simplify a matrix. Can you likewise simplify a system? Yeah, totally. That's exactly what we did here. So roughly speaking, and to keep in mind that P matrix, that's a change of basis matrix, right? That terms, switching from S coordinates to V coordinates, that turns a matrix we don't like into a matrix we love. And likewise, that same change of basis matrix, conjugation, I should say, by that same change of basis matrix, turns a system that we don't like into a system that we do like. Last observation I want to make, real quick before we go on. Let's see here. So Z is P inverse Y. Let's come down to here. Z is P inverse Y. That means that Y is equal to PZ. And let's see here. Let me get this out of the way now. I'm going to give myself a little bit more room. Let's put this up there. Another way to say this is, don't forget P is a change of basis matrix from V to S. Here, let me color code. P is change of basis from V to S. So if you interpret, very reasonably, if you interpret Y as being standard basis coordinates, then very reasonably what that means is your Z is just V coordinates of the same solution. If you think of your solution as being, not a list of independent functions, right? Don't think of it as being y1 through yn. Think of it as being literally vector-valued solutions. Vector not in the intuple sense, but vector in the abstract vector sense, right? Then what this conversion does, the relationship between y and z is, well, y are standard basis coordinates for that abstract solution, and z is just the same solution, just in a different coordinate system. All right, and last comment on this before we go on, do a bunch more details. P is a change of basis matrix, and that basis is the basis of eigenvectors. Right, so eigenvectors are the tool that makes this all possible. So, linking this back up to section 5.4, why do we care about eigenvectors? There's a long list of reasons. Right? But as far as this class is concerned, one of the big ones is we like eigenvectors because it gives us the ability to simplify matrices, and we like to simplify matrices because it allows us to simplify systems of differential equations, and we like that because this is something we actually know how to solve. Eigenvectors gave us this. Everybody on board? Questions? Feel free. Okay. Alrighty. Okay, so details to come. So now we've gotten it down to here. Diagonal system. Here it is. There's our decoupled, a bunch of equations, none of which have anything to do with each other. Now let's actually write down the solutions. We've done some of this. We've talked through some of this already. So that natural growth, right? Solve for Z1. It's easy. It's Calc 2, and likewise for the other equations. There's your C1. Again, Calc 2. Right? There's your Z2, et cetera, and there's your Zn. So these are all your solutions. Those are your Z solutions right there. I'm going to write that a little bit differently. Keep in mind, these are all coordinates, Z1, Z2 through Zn, et cetera. That means, since I know all the coordinates, I can write that same thing in vector form like this. Notice the coordinates, right, are those coordinates that we've got written down up there. So that's just a rewrite. I didn't really do anything. Don't forget as well that coordinates are coefficients in linear combinations of the standard basis vectors. Right? So if I want to rewrite this vector, instead of writing it in a bunch of coordinates, if I want to write it as literally a linear combination of standard basis vectors, there's that. That's a chapter 1 move. It's arguably a math 212 move, right? To rewrite it like that. And then, having rewritten this as that, I can then move parentheses around a little bit. And notice I have now arbitrary linear combinations of these vector-valued solutions. So those vector-valued solutions, that's a fundamental set of solutions. Fundamental set of solutions to our original system. And the nice thing about having it in this form, nice thing about having it like this, is now this is in the language of linear algebra, right? We're talking about vectors and bases instead of just a bunch of coordinates. Okay. So again, I didn't really do anything much there. This is just changing I'm kind of dancing around, remanipulating how to write the solutions that we already had in effect at the top of this page. Is everybody okay with that? How do you feel about that? Yeah? Yep.
What are the E's referring to?
Standard basis vectors. So this, let me write it down. This E1 is just a 1 followed by a bunch of zeros. The usual, E1, E2, E3, like IJK from Math 212. Yeah, totally. Yep. Okay. Okay. Now, a lot of students will spike the football right here. That's no good. What we have here are solutions to the wrong differential equation, right? This is the z equation. This gives us what you might say the v coordinates of our solutions. We want to know the s coordinates. We want to know the standard basis coordinates. We want to know the y's, right? We have found the z's. We want to know the y's. Okay, we've got to solve. Then, of course, that's not that big a deal. The way we solve for y in terms of z, that's just a multiply by p. Or, again, you might think of this. I think it's more intuitively satisfying to think of this as just do the change of basis, right? Z is the v coordinates. Y that I'm looking for is the s coordinates. Do the change of basis from v to s, which of course is what p does. So in doing this now, just keep in mind, how do we multiply a p matrix times these solution vectors? Notice that in doing this, we're going to be I kind of made a mess here. Let me do this. I'm going to come way over here. There we go. Don't forget that our P matrix is made up out of eigenvectors. Right? So when I multiply P times Z, I'm taking a matrix that's full of eigenvectors and I'm multiplying it by a bunch of standard basis vectors. And there's some scalars. Those exponentials are just scalars. Right? So matrix times standard basis vectors give you columns. The columns, again, we already know, are eigenvectors, and so multiplying that out, I get these eigenvectors here. Okay, and so we're done. So our y fundamental set of solutions is this list of functions right here. And so, what's that? 3 pages in, we finally have an answer, right, to a diagonalizable system. And the good news, though, is note we made very, very few assumptions in this calculation. I call it a calculation. Really, what we've done is we've derived a theorem, right? We're assuming only that this matrix is diagonalizable. That's it. Assuming only that it's diagonalizable, everything else is fully general, and so we have a theorem here that says that whenever you have a diagonalizable system, if you know the eigenvalues and if you know the eigenvectors, right, then per the argument on the previous page, the previous 3 pages, the eigenvalues are coefficients and the exponents that you then multiply by the eigenvectors, pairing up appropriately, of course. Let's see here. right? Pair them up appropriately, but e to the power of lambda x times the eigenvalues, the eigenvectors v, those are your fundamental set of solutions. And it works for every diagonalizable matrix. And it makes it for an awesome theorem. So good news, you really don't have to go through this whole calculation every time. Every single time you do one of these, I would like to solve this diagonalizable system, you can just say, oh, well, it's diagonalizable, eigenvalues and eigenvectors, therefore done. Okay. So for example, let's suppose you're interested in this system. By the way, we were interested in this system. This was the system that I talked about last time, and I pulled a couple of solutions out of thin air. Right? No evidence where they came from. I said these are magic solutions. Let's just observe. Let's take those as granted. Right? Notice that they're independent. Dimension argument. Talk about bases and spans and declared victory. So, where did they come from? Well, the eigenvalues, the eigenvectors. That's an old calculation. Now, if you encounter a matrix where you don't already know the eigenvalues and eigenvectors, okay, you're going to have to do that, right? You have to go through and play the usual game, take the matrix, characteristic polynomial, roots, a minus lambda I, null space, that whole shebang. Find the eigenvalues and eigenvectors and declare victory. So, notice the eigenvalues go there and there. The eigenvectors go there and there. Paired up appropriately, of course. And there's your fundamental set of solutions. Or if you want to write this as a general solution, you just take the span of those fundamental vectors, and so there's your general solution. Same thing. Take your pick. It doesn't really make much of a difference. Okay. How are we doing? Everybody happy with that? Okay. So I want to make a suggestion for y'all to do. You don't have to do this, but I think this would be a really great idea. If you would like to check your understanding of where all this comes from, right? And keep in mind, I cannot emphasize this enough. This is not a class about answers. This is a class about ideas, right? And so on the exams, don't expect that all you have to do is compute. And sometimes you got to prove things, or you got to make an argument, talk about why does something work, not simply that it works. So it's important that you understand where this argument, how this argument works, where everything comes from, right? And if you want to check whether you understand this argument, a really direct way to do that would be to take this matrix with these eigenvalues and eigenvectors and go through the original argument. Don't just cite the theorem like I did here, but think about, okay, well, what would a diagonalization of this matrix look like? How would you rewrite it? How would I write the relationship between y and z? What is the z equation? Solve that z equation explicitly in each coordinate. Write down those solutions. Put them in vector form. That whole process that we went through. Go through and do that specifically for this question. And of course, that your goal, what you should end up with is that. And just make sure that you get down to that as a right answer. So I think it'd be a really nice exercise. And I guess this is a pretty good stopping point. Looks like we're not quite out of time, but let's go ahead and call it a stopping point anyway. See y'all later. Have a good day. Have a good weekend.